All right, we're going to continue our discussion on simplifying radicals. If you take out the same notes paper from yesterday, but actually flip it over, if you flip it over to the back side, what we're going to do is we're going to talk about a new rule. That new rule is the quotient rule. Now, quotient is really just a fancy word for a division problem, which really is a fraction. So, yep, now we're going to take a look at how to use, how to simplify radicals when we have a fraction. Now, the quotient rule says that if I am taking the nth root of a divided by b, well, that would be the same thing as splitting this and taking the nth root of the numerator, which would be a, divided by the nth root of the denominator, which would be b. So it is a similar rule to the product rule. Essentially, it says that we can split a problem up into two. And of course, we can also go the other direction. We can take two and we can pull them together to be one. All right, so you ready to take a look at some situations? The first one we're going to look at here, I would suggest in the upper left corner, we're going to call it basic. These kinds of problems will be basically pretty straightforward with using the product quotient rule. All right, so when you're ready, let's consider something like this. The cube root of 3 divided by the cube root of 81. Now, we want to be careful and understand that there's really nothing you can do as is. You can't do the cube root of 3. Don't say that that's 1. In other words, we're looking for three numbers that would multiply to be 81, and those numbers don't exist either. Don't say 9, because it only takes two 9s to get 81. Three 9s is going to be more than 81, and we wouldn't want to do something like, say, 3, because that doesn't get you far enough to 81. So there's no cube root of any of these problems, but the interesting thing is if we apply the quotient rule, you can take two, that is two radicals, and you can make it one. You can make it one radical. Now, what this also does is allows us to actually do some math. Like we can do 3 divided by 81, or maybe we should say we can reduce 3 over 81. Now, just like any fraction, 3 over 81 reduces 3 times in the numerator to be 1, and in the denominator to be 27. So we reduce that fraction. Now, can we split it back up into 2? Well, sure. And what's happening here is we're actually using the quotient rule in both directions. Now I split it back up, but the main reason I did that is because now you can actually do the cube root of 1. The cube root of 1 is 1, okay? Because 1 times 1 times 1 is still 1. But how about this one? How about the cube root of 27? Well, now you're looking for three numbers that multiply to be 27, and we've known those three numbers to be 3. So we're able to simplify this to be 1/3. Notice that there's no radical in my final answer. I also have made it into smaller numbers, so it is simplified. Let's take a look at another one. Just call it an example. How about if I want to do the cube root of 16a squared times b over 2a squared b to the 4th. So we want to do the cube root of this fraction. Now, be careful that you don't just do what we did in the problem before, just because. In other words, we don't always just follow the exact same steps. I wouldn't expect you to split this up. Rather, I'd like you to notice that you can actually do some math underneath here. You can actually reduce. You can do the fraction. You can take 16 divided by 2, and 16 divided by 2 is 8. You can cancel the a squareds just because they do cancel. And it looks like the b's, well, you can do a little bit of reducing with those. Now, this is b to the 1st divided by b to the 4th. What really happens is the b to the 4th is going to cancel with that b to the 1st and leave us with just b to the 3rd. It's only going to leave us with 3 b's down there. So we did a little bit of canceling, we did a little bit of reducing, and the interesting thing is now we have ourselves the ability to actually do the cube root of 8. And we have the ability to actually do the cube root of b cubed. So now we can split the problem up using the quotient rule into two radicals. And you know the cube root of 8, right? How many or what number can I use 3 times to get the number 8? Well, it would be 2, because 2 times 2 times 2 is 8. And what about the cube root of b cubed? Well, like yesterday, we talked that we can take that b cubed out because we'll divide the 3's. When you divide those 3's, you get 1. That is, you get b to the first power, b to the 1. You don't have to write that 1, but that's what I get when I divide those 3's. Alright, you ready to try one of these on your own? This would be a good time to pause the video, see if you can work out the cube root of 128 divided by the cube root of 2. And then when you're ready, play the video and see how you do with the problem. But I encourage you to try it now and play it after you've tried. All right, how did you do? We want to understand that as is, you can't do the cube root of 128. It's not a perfect cube root, but you can pull this together to be one radical, that is one cube root of 128 divided by 2. Now that's using the quotient rule, and the nice thing about that is you can do some math. We know that 128 divided by 2 is 64. Now that we have a new number, now that we have this 64 here, can we do its cube root? Well, yes, we can, because there are 3 numbers that multiply to be 64. What are 3 numbers, and they have to be the same 3 numbers that multiply to be 64? Right, it would just be 4. Now, what happened here is I was able to pull the entire 64 out as a 4. There's nothing left behind because 64 is already a perfect cube root. So again, our final answer is just 4. All right, so we're going to move on to the next situation that involves a quotient rule. Just going to be honest with you, this is not easy. It wouldn't be easy if we were in the classroom, and it doesn't make it any easier that we're apart right now, but you can do it. You're going to have to try again, and eventually you can be victorious. But again, it's going to take a good attitude and a desire to try to figure out what it means to rationalize a fraction. Now, maybe you've never even heard of the idea to rationalize a fraction, although I would bet that you did a little bit of it in algebra. This is usually a very new idea for kids. So again, we're in this together. Rationalize. What does rationalize even mean? Well, you're going to find out it means that we don't want a root in a denominator. We don't want a root in a denominator. So here we have the cube root of x squared over y. And just to be clear, it's the cube root of all of this. So it's the cube root of the entire fraction x squared over y. Now, it doesn't look like there's much that we can do. We can't simplify anything. You can't do any math, so we really have no choice but to split this up into 2 separate roots, just like we were doing in the last section. So we'll split this up to be the cube root of x squared divided by the cube root of y. Now, it doesn't seem like a big deal, but it is. You see, here we have a root in a denominator, and that is a no-no. We don't want a root in a denominator, in this case the cube root of y. So what are we going to do? Well, I'll fill you in a little secret. What we're going to do is we're going to make this denominator look like y to the third. Now the reason we want it to look like y to the third, I hope you can see that this will eventually cancel and it will become just y. So if we can just make it look like y to the third, then we'll be able to do this canceling and get rid of that radical. So how do we do that? Well, we can't just write it, but we can make it, we can multiply it. So we can't just write it, but we can multiply it. And what we're going to do is we're going to multiply the top and bottom of this fraction by just the right amount of y. That is the right amount of more y. You see, right now we have y to the first. You might say we have 1y. Well, we need 3, so that means we're going to want 2 more. We're going to want 2 more. So we're going to multiply the top and bottom by y squared. Now, this is the key to this problem. And the reason that I'm multiplying by y squared is because I start with 1 and I would like 2 more. And the reason I would like 2 more is because, remember, we want to make the denominator look like y to the third. And that's exactly what we're going to get when you multiply the y's in the denominator. Now, up in the numerator, it changes. It also changes. And the reason it changes is because we are multiplying by this root of y squared. But it doesn't have to be too tricky. The only thing that really changes here is that we had our x squared to begin with, and now we just bring this y squared along with it. So we multiply the top and bottom by the cube root of y squared. Now, believe it or not, this is better. This is better because the cube root of y cubed cancels to just be y. And remember, we don't want a radical in the denominator. Well, we don't have it anymore. We do have some new stuff in the numerator. That is, we have the cube root of x squared y squared. This is your final answer. It's a better answer. Even though you might think that it looks more complicated, it's actually better because we rationalized. And to rationalize means to get rid of a radical in the denominator. Let's try another one. I don't expect that you're an expert on it after just one problem, but I think you'll find that there are some similarities. So how about x squared, or excuse me, the cube root of x squared over 5? The cube root of x squared over 5. Okay, so there's nothing we can do. We can't actually divide these numbers. We can't change it. So the only choice is to split it. And you split it into a root of x squared in the numerator and a root of 5 in the denominator. Now, that root of 5 in the denominator, that's not good. We don't want to have a radical in the denominator. So what we're going to have to do is we're going to have to multiply by just the right amount of 5s. Now, this is the key to the problem. You see, we have 1 5. We have 5 to the first power. We want how many more? We want how many more? Well, the answer is we always want to end up with the same amount that is this root. So I want 3 5s, but that means I just want 2 more. So we're going to multiply the top and bottom by a root of 5 squared. Now, something that's happened now in these two problems that I'd like to summarize with you, and that is we always want to multiply by more denominator. And the amount that you multiply by needs to come out to equal the total root. So we want to multiply by more denominator so we can equal the total root. Looking at this problem one more time, the total root was 3. It doesn't matter which 3 you look at, the total root is 3. So that means we want to multiply by more denominator. But how much more denominator? Well, we only needed to multiply by 2 more, okay, because we already had 1. So we multiply the top and bottom by a 5 squared. Now, when you multiply the top and bottom by the 5 squared, some things change, all of them for the better, but let's be aware of what changes. We now have 5 to the third. And as we've said a couple times, we want these numbers to be the same so they can cancel. If you look in the numerator, though, we get some new numbers. We actually get the value of 5 squared. Now, the value of 5 squared is 25. I'm going to change that to 25 because that's simpler than looking at 5 squared. So in the numerator, we get something new. In the denominator, we're ready to cancel. We're ready to cancel the 3's, okay? Because basically the cube root cancels with the exponent, leaving you with just the number 5. Just the number 5. Now the numerator, we already changed that, so it's the root of 25x squared. Again, we rationalized because the denominator no longer has a radical. That means it's been rationalized. Ready to try one on your own? Okay, I told you it's a little tricky, but I'd like you to try to rationalize the square root of 3 over x. Now, as you work out this problem, keep in mind that this is a square root, so that means that the root, the number that we're trying to achieve, would be the number 2. All right, how did you do? Just like the other problems, we really have no choice but to split it up. Now, the square root of 3 over the square root of x, the square root of x in the denominator, that's not allowed. You're not allowed to have a square root in the denominator, so we're going to have to multiply. We're going to multiply the top and bottom of this equation by more denominator. Now, how much more? How much more? Okay, we want to get the number 2. We want to get the number 2. Right now we have 1. We have x to the 1. So how many more x's do we need? That's right, we just need 1 more x. Okay, we just need 1 more x, which really means that we're multiplying the top and bottom by the square root of x. Now, when you do the denominator, you end up with the square root of x squared. The square root of x squared. That's nice because that's going to cancel. When you do the numerator, you end up with the square root of 3x. So, when you're ready to cancel the denominator, you end up being able to say that you have the square root of 3x over a canceled denominator of just x. Okay, again, what's happening is this blue 2 is canceling with this green 2, and it leaves us with no more square root. All right, on we go. We're going to take a look at another situation here. I'd suggest using the lower left corner. They're going to be multi-step problems, multi-step. All right, so let's take a look at it. Just kind of consider with me. Whenever I say consider, I'm suggesting that there might be some things that you already know how to do, but I want to help you figure out how to put this all together because there's going to be multiple steps. How about the cube root of 16 over x to the 10th? The cube root of 16 over x to the 10th. All right, so how about we split this up? It's kind of the natural thing to do. It's called the quotient rule. But interesting, when you split this up, you find out that you can do some of these roots. In other words, remember how yesterday we were splitting we were splitting 16 into 2 numbers. Now you want to split it into 2 numbers, one of them that has a perfect root, so we could split it into 8 and 2. 8's going to kind of be our magic number here that's able to come out. But you can also think of splitting up your x down here. This time you want to think about the highest number that divides that's inside of 10. The highest number that divides by 3 that's inside of 10 is a 9. So we split this into x9 and x. And it's going to be our x9 that's able to come out. All right, so what happens when you bring these numbers out? Well, you do the cube root of 8. The cube root of 8 is 2. Of course, it leaves behind this 2. How about the cube root of x9? Now, when you do that, you divide, so you end up with x3. The x stays behind. Now, it's a nice job, but it still has a problem, and the problem is there is a radical in the denominator. Shucks, you can't have a radical in the denominator. So now what we got to do is we got to multiply by more denominator. We got to multiply the top and bottom by more x. Now, how much x do you want? You want 3. How much do you have? You have 1. So how much more do you need? You need 2 more. So you multiply top and bottom by x squared. That is the cube root of x squared. See how that works? Now when you multiply these green, well, really you're going to add those green numbers, but when you put those numbers together, you're going to end up with a better denominator. Okay, now, yeah, let's make the denominator. Some things in the denominator would be that the x cubed that was in the front is still there, but now we end up with x3, and that x3 is going to cancel with this root of 3. Now I was getting a little ahead of myself here. The numerator, we also get some new numbers, namely we just pull together that 2 and that x squared. So we'll pull them together and we'll get the root of 2x squared. The canceling that happened down here leaves you with just x, but that's able to combine with this x cubed. And so how many x's do I end up with when you combine these? Well, we end up with x to the fourth. X to the fourth in the denominator, and then our numerator, I'm going to have trouble squeezing it here, but it stays the same, 2 the cube root of 2x squared. Multi-step. Why don't you try one? Okay, I encourage you to try it. This is an opportunity. It's actually a little easier than the one that I just gave you, but it's an opportunity to push pause after you write down the square root of x7 divided by 3. So it's the square root of x7 divided by 3. All right, how did you do? Split it up. Really nothing else that you can do. Now, once you split it up, you want to recognize that there's something you can do with this square root of x7. That is, you can take out a lot of that x. You should be thinking that you can take out 6 of them. Now, when you take out 6 of them, or when you think of it as x6 times x to the 1, and you take out 6 of them, remember you're going to divide that by 2. That is this 2, this square root of 2. So we're going to end up, so we take out that x6, and we end up dividing it to be x3. It leaves behind the square root of x. Well, now we got to do something with the denominator. Now, the denominator has a square root of 3, so we're going to have to multiply the top and bottom by more denominator. How much more? Well, maybe the better question is first, how many 3's do I need? We need 2. How many do we have? We have 1. So how much more 3 do I need? That's right, you need just 1 more. In other words, you need 3 to the first, or just 3. Now, when you multiply those denominators together, you're going to get 3 squared. 3 squared is going to cancel with the root of 2. And of course, when it cancels, it's going to leave us with just 3. You can skip to that step if you're ready to do that. If you look up here in the numerator, you've got some numbers you can pull together, namely the square root of x and the square root of 3 will now be able to become the square root of 3x, so just kind of pull them together. How about this x cubed that was out front? It's still out front, so make sure that it gets part of your final answer. So we end up with x cubed, the square root of 3x, all over 3. All right, which gets us to our last category, which is plain and simple super. Super tough? Nah, we'll let you decide, but it definitely is a super category because it does have quite a few steps. Now, this is something we're going to work towards. This problem, don't expect you to have it all figured out the first time, but we're going to work towards the answer, trying to figure out how to do something like simplifying 7 times the cube root of 48y to the 7th divided by the cube root of 2y squared. So when you're ready, after you copy it down, let's continue. Now, it looks like that we've already split up the radicals, and if you start to inspect what you have, namely the numerator, you have some things you can break down. Just like we've done the last couple days, you can split up 48. Now, to split up 48, you want to be trying to think of some perfect numbers inside of 48. 8 is inside of 48. Now, that would leave behind a 6. But the reason I'm using 8 is because 8 is a perfect cube root. Now you could also split up the y7. Here you want to think about the largest number inside of 7 that divides with this 3. And I hope that you're coming up with a y to the 6, which still leaves behind just a y. Now, we're going to change one thing at a time, so everything else stays as it is. The 7 out front, the denominator, but now we're ready to bring this 8 out. We're going to bring the 8 out, and it turns into a 2. Now we're ready to bring this y6 out. And when we bring out y6, it turns into, well, it divides, remember, it divides, and it becomes a y squared. What's left behind? Well, I believe that we still have a 6 left behind, and I believe we still have a y left behind. Now, you haven't seen this yet, but can you guess what's going to happen with these two numbers? Well, yeah, you're going to multiply them. So we can multiply those, and we can get 14. For sake of space, I'm going to go ahead and just change them to 14. But now I'm staring at 14y squared, the cube root of 6y, and divided by this cube root of 2y squared, which now is our problem. Remember, you can't have a radical in the denominator. So it's time to multiply by more denominator. Now, are you starting to catch on? Okay, the question is, how much do we want? 3. How much do we have? Well, right now we have 2 to the 1. So that means how many more 2's do we need? We need 2 more 2's, because that's going to give us a total of 3. How much y do we need? We need 3. How much do we have? We have 2. So how much more do we need? Well, we need just 1. So we're going to multiply top and bottom by a 2 squared y. We're going to multiply by a 2 squared y. Now, after you do that, you get a better denominator, a denominator that has 3 2's, a denominator that has 3 y's. And yes, yes, and yes, those are going to cancel. If you're ready to do that, you can jump ahead and just write down 2y, okay? Because all the radicals and all the exponents cancel. Now, there is some business that happens up here in the numerator. First of all, in the numerator, 2 squared is really the same as 4. So I'm going to change that to 4 because I want you to see that this 4 is going to be able to multiply by this 6. Well, that's kind of nifty. That's going to give us a new number under the radical, of course, 24. These y's, they're going to interact. They're going to multiply together. And yes, that's going to give us some new y's. It's going to give us a y squared. Now, I didn't do anything with this 14y squared out front, but don't forget about it. It's still out front. Now, there's something else that we can do. Yes, that's right. There's a perfect number inside of 24. It's the perfect number of 8. That's because 8 times 3 is 24. So I can pull this 8 out, and when it comes out, it turns into a, well, as it's done many times, it turns into a 2. That's because that's the cube root of 8. Now, look what we have here. I think we still have a 3 left behind. We still have a y squared in that numerator. But now we're actually able to cancel the denominator just by basic fraction canceling. We're able to cancel these 2's, and it's actually been true that we're going to be able to cancel these y's, at least part of them. So look, you're not left with any denominator anymore. The denominator completely cancels out, and we're left with just 14y, the cube root of 3y squared, and that is indeed a super problem. I don't want you to panic. You're not going to get a quiz on that tomorrow, but it is something that if we do each step carefully, we can simplify, pull out perfect numbers, and in the end, we even did a little bit of canceling to get rid of the entire fraction. You're ready to try the homework, and just like in the last lesson, I'll provide an explanation of the homework, but don't watch the explanation until you try the homework. You got to try it, and then you can watch the explanation and see how you did, and I'll even provide you with some other practice opportunities, and we'll keep working on this even in the next lesson.